In this video, we're going to look at another recursive algorithm, or another algorithm that's also often implemented recursively. It's our old friend, the binary search algorithm. Let's just refresh our memory about what the binary search algorithm does. Binary search is useful if we have an array of values that are stored in sorted order, so smallest to biggest or biggest to smallest. We just have to know which way it's sorted. And then we're looking for a key value within that collection. And our binary search algorithm is going to return a -1 if the key is not found, and it'll return the index where the value is found otherwise. So if we have an array, let's look at a code example. If we have an array that has 1, 3, 5, 7, 9, that's in ascending order, so that's cool. And if we were looking for the value 5, it would return 2 because that's the index of the value 5, 0, 1, 2. If we were looking for the value 7,000,006, it would return -1 because that's not in the collection. So earlier in the semester, we wrote a non-recursive solution using a while loop. And that's totally cool. You can implement that and it's no problem. Sometimes people think of the binary search algorithm in terms of a recursive solution. We're going to see if we can build that today. So when you're thinking about a recursive solution, remember that your first step is to identify the base case and the recursive case. So you want to take a minute and pause the video and think about that. What's the base case? When do you know the answer without doing any work or processing? And then you also want to think about, when do you not know the answer? When do you have to do more searching in binary search? This one's a little bit more complicated than the previous recursive example we looked at, in that this particular time, there's more than one time that we could stop without processing further, and there's more than one way to continue on in the recursive case. Pause the video for a minute and see if you can think of those situations. So one of the reasons that we might be able to stop processing and return the solution is because we found the number. So we're comparing the key to the index in the array at the middle position. Remember, the binary search algorithm always looks in the middle of the array. So if we compare the key to the middle of the array and they match, that means we found it. We want to return middle because we want to return the position where the value was found. In this case, if array at index middle is equal to the key, the index where it's found is middle. Another time where we would want to stop searching without doing additional work is if we know that the item's not in the collection. So if we've searched through everything possible, there's no possible way, there's no other values that we need to consider, then we know the item's not in the collection. So in that case, that happens whenever the value of first is bigger than the value of last. In the array. So it's a case where we know that the item's not going to be part of the array. We've already searched through all the potential values. If the key is not found, we want to return -1. It's going to be the value that we return in that base case. So two different base case. One, when we find it, we want to return middle, and one where we're confident that it's not in the array because we've searched all the possible places. In that case, we want to return -1. So now we want to turn our attention to the recursive case. When do we know we want to do more searching? Remember in the original binary search algorithm, if we compared the value to the index middle and it didn't match, then we had to consider, like, do we want to look just in the first part of the remaining list, or do we want to just look in the last part of the remaining list? So the two possible additional cases that we haven't covered yet are if the key is less than the array at index middle, and also if the key is bigger than the value at the array at index middle. So if there's like valid stuff left to search, then we'll need to make a recursive call. We want to call binary search. And we think of the binary search algorithm as needing those 3 indices that help us keep track of what part of the array we're searching: the first, the middle, and the last. Then whenever we're searching and the key is less than the current value of index middle, that means that the part of the array that we're searching at position middle is bigger than anything that any place that the value could possibly be located within the array. So we want to make the last cutoff be middle minus 1. So we're going to call with first. Actually, let's not cast middle. Let's just put first and last. So we're going to call it with the same value of first, because it still could be towards the front of the array. But now instead of the current value of last, we want the new value to be middle minus 1. Because we only want to search the first part. Similarly, if we're looking at a key value and it's bigger than the middle value in the array, then we want to only search the end of the list. So we want to start at middle plus 1 and end with the same value of last. So those are going to be our kind of guidelines for our algorithm as we create it in Java. We want to code those same 4 possibilities. Those are what can happen in our code. So I already coded part of it for you. I created the main program where we have this little array and we get the key value. I just stored it as a literal, but you could make it be user input if you wanted to. And then we're going to make a call to the recursive binary search algorithm. Just like I did in the examples, I'm going to keep track of first and last. Those are 2 of the arguments that get passed in. I also have to pass in the whole array of values, and I also have to pass in the key. So here I'm passing in the array first, the length of the list, and key. That's going to match up with these parameter values that are expected: the list, the first index, the last index, and the key that we're looking for. All right, cool. So I'm going to code some of the base case first. I want to see if, let's do this one. This one's pretty easy to code up. So if the key that we're looking for is in the middle of the array, so I'm going to have to calculate middle first. And middle equals first plus last. Divide by 2. So it's just like what we did in the non-recursive version. We had to calculate that value. So here I'm checking to see if the key is equal to the value at position middle. If it is, then I want to return middle. That means I found it. Otherwise, if the key is less than the index middle, else if key is less than the list at index middle, then that means I want to make a recursive call I would call it with, I called it recursive binary search. Recursive binary search first, middle minus 1. Oh, I have to put the list in here too. I'm going to call it list first, middle minus 1, and then the key value. If the key is greater than the listed index middle, then I want to make my recursive call with middle plus 1. And the key. Awesome. And so I've coded 3 out of my 4 cases. The one that I didn't cover was if first is greater than last. I only want to do these if first is less than or equal to last. It's going to go around all of this. And then otherwise, I want to return -1. That means I haven't found it. So again, in this case, if first is less than or equal to last, that means we want to do all of these checks for the various key positions. If first is greater than last, then we'll just go down here and return -1. So now we've handled all the possible values for our recursive search. Let's try it out. We got 2 different calls up here. One's looking for the value 3, which should be in the list at position 1. And then we're going to search for 2. That's not going to be in the list, so it's going to print -1 as my result, we hope. All right, so I've got a parenthesis, and I got an extra parenthesis. All right, cool, now we're going. So was 3 in the array? Yes, it was found at position 1. And then was 2 in the array? It prints out -1. And again, that means it wasn't found. So it looks like our recursive binary search algorithm is working. If you wanted to, if you were curious about the call stack trace and how things work, you could add a debugging breakpoint right here, and then you could use that same process we used last time where you compiled with the debugger and you trace through all the code, and you could draw your own call stack trace that shows the various values that get added to that.